This video describes soil sampling in general and field meters suitable for analyzing soil. Soil contamination should be assessed, for example, when new operations such as construction will begin in the area. Soil assessments may also be required after accidents, sometimes urgently, to identify pollutants and prevent them from spreading. When examining soil contamination, it is important to find out what contaminants there are in the soil and what are their environmental concentrations. If the soil is found to be contaminated, the necessary remediation can begin. The type of soil plays a major role in how water and contaminants behave in the soil. For instance, sandy soil does not retain water, meaning that contaminants can easily travel through the soil. By contrast, clay soil, with a much smaller grain size, retains water and contaminants well. Groundwater aquifers also have a major effect on how contaminants migrate. You should always check if the target area has groundwater deposits. The properties of different compounds affect how they migrate. These properties include volatility, water and fat solubility, sorption, and the decomposition of contaminants in the environment. When planning sampling and suitable methods, you should assess where the target contaminant has most likely migrated to. Knowing this, you can then start considering the best way to study the concentrations of contaminants and, for example, the right depth for taking samples. For the sake of occupational safety, the toxicity and possible location of the contaminants should be known already during planning. Protective equipment should always be appropriate for the situation. In some cases, gas detectors, for example, are essential and can save lives by alerting users to harmful gases in the air. Soil sampling also always requires the landowner's permission and any other required permits. In soil sampling, the locations and number of sampling points are crucial to the representativeness of the results. Contaminants are not usually evenly distributed in the soil, and sampling may require the study of large areas in one go. The number of sampling points depends on many things, such as the purpose of the study, the acceptable uncertainty of the results, and the available resources. It is also important to decide if you want to point or composite samples. Due to the heterogeneous nature of soil, composite samples usually portray contamination better than point samples. In composite sampling, several, up to dozens of incremental samples are complied from the target area and combined into one sample for analysis. The sufficient number of sampling points and their location and the sample quantity should always be decided based on the site. The sampling may be, for example, random, systematic, or based on previous contamination data. The approach and model to use should always be considered case by case. The aim is to produce representative and sufficiently comprehensive data on the target area. There are several methods for soil sampling, and their suitability should always be considered based on the properties of the soil and the contaminant. Typical sampling methods include, for example, excavation of ground, that is, digging trial pits, mechanical or manual sounding or boring, taking samples from soil piles or windrows, or digging directly from the topsoil. When taking samples, the suitability of the tools for sampling should always be evaluated. For example, when studying metal content, metal tools should be replaced with plastic or glass tools to avoid contamination. However, in practice, it may be hard to dig with anything but metal tools, in which case their potential influence on the results should be considered. The suitability of the sample containers should also be evaluated. Not all containers are suitable for all samples. Typical containers for soil samples include glass containers, gas-tight plastic bags, and Teflon-coated vessels. All the other tools that are in contact with the samples, such as the shears, should also be clean to avoid contamination. Whatever the soil sampling method, the sampling should be documented in a record and the samples protected from light and temperature variations during transport to a laboratory for analysis. In some cases, samples should also be fixated so that the concentrations of the studied contaminants do not change. The samples must remain unchanged until the analysis. The order of sampling should be arranged so that sampling starts from the cleanest area and proceeds to the more contaminated areas, from the lowest to the higher concentrations. This prevents contamination between sampling points. The properties of the target contaminants should also be examined when considering the order. For example, volatile compounds should always be sampled and fixated first, because they volatilize quickly. In some cases, assays should also be done directly in the field. Soil samples can also be analyzed directly and the site using field meters and analyzers. Some meters only provide general suggestive mean results, whereas others provide more accurate contaminant-specific results. The suitability of the meters for the target site should always be considered case by case and based on the aim. The results of field measurements should also be verified by laboratory analyses, and the meters should be maintained and calibrated often enough. Next, this video will describe several field meters for studying the soil. The PID, or photo ionization detector, is a field meter for measuring the sum concentrations of volatile ionizable compounds. The device sucks in the target air in an ionization chamber where UV light turns organic compounds into positive ions. The device recognizes the amount of energy released in ionization and displays it as the concentration in air. The meter is calibrated to two parameters: zero concentration, or the ambient air, and the known concentration of a gas detected by the device. Before use, the device is reset to ambient air or through a special carbon filter. Measurements can be taken directly from the soil or, for example, a gas-tight bag containing a soil sample. The gases move from the pores of the soil sample into the bag where they can be measured with the meter. The measurements are influenced particularly by the temperature, soil density, humidity, and the time the sample has been exposed to air. It is also important to note that the results are some concentrations of all ionized gases volatilizing from the soil. If we know the volatile compound in the sample, we can choose the appropriate response factor in the device, which improves the reliability of the results given. Geotech GA5000 is a portable gas analyzer that can be used, for example, to measure landfill and biogases. The device can detect methane, carbon dioxide, oxygen, carbon monoxide, hydrogen, sulfates, ammonia, and hydrogen. The detector can be used together with a separate sampler that is inserted into a compost pile, for example. The device sucks in gases from the sampling point and displays their concentrations on the screen in real time. The measured values can be saved in the device's memory and later transferred to a computer for closer inspection. Petroflag is a turbidimetric field analyzer for inspecting the total petroleum hydrocarbons in soil samples. The method can be used, for example, in the survey and remediation projects of contaminated areas, oil spill response, and the disposal facilities for oil-damaged soil. Petroleum hydrocarbons are extracted from a 10-gram soil sample with a methanol-based solvent, after which the liquid is filtered into a developer fluid. The hydrocarbons contained in the sample cause a chemical reaction that causes the solution to become turbid, and this turbidity can be measured. The device shows the result as the total petroleum hydrocarbon content, so it does not measure petroleum hydrocarbons alone. The results therefore also contain the natural carbon content in the soil sample. The method is particularly well suited for mineral soils, because the natural carbon in soil is a major source of error in the results. The method is suitable for commonly used petroleum hydrocarbons such as fuels, motor oils, lubricants, and kerosene. Each of these substances can be assigned their own response factor in the analyzer, improving the accuracy of the results. X-ray fluorescence, or XRF, is a non-destructive analytical technique used to determine the chemical composition or metal content of materials such as soil samples. The heavier the element, the more reliable the results of the device. The device is therefore well suited for heavy metal analysis. Since the device emits X-rays, the user must be trained and qualified to use the device. Wearing a lead shield while taking measurements is particularly important. The X-rays also pass through the measurement platform, so the measurer's legs and feet should not be below the sample, such as under the table. Humidity, organic carbon, and the heterogeneity of the sample affect the reliability of the results. Reliability can be improved by pre-processing the samples. Pre-processing involves first sieving out large objects, such as stones and, for example, bullets, after which the sample can be homogenized and dried to remove moisture. Samples are not usually dried in field conditions, resulting in a higher measurement error in the results. The analysis itself can be done through the sample bag. The device sends X-rays to the sample and identifies the fluorescent radiation it emits. This fluorescent radiation is characteristic for each element, allowing the device to identify the elements in the sample and their concentration. To ensure the reliability of the results, it is recommended to take several parallel measurements of the same sample and give the mean value of these parallel measurements as the final result. There are therefore several different methods to study soil contamination. But since the properties of the sampling sites and the aims of the studies vary greatly, the suitable methods should always be evaluated case by case. Whatever the method used, it is important that the achieved results are of high quality and compatible with the aims, and that they allow the necessary conclusions to be drawn to assess the state of the soil.